Hello guys, welcome to DMS AI EduTech and welcome to another video of DAA subject complete notes. So in the last video I have explained completely about what is an algorithm and performance analysis of algorithm, time complexity and space complexity. First you watch that video, last video, and then come to here. So you can easily understand what is meant by complexities and what are the asymptotic notations. So in this video, I'm going to completely discuss about what are the asymptotic notations and what is meant by an asymptotic notation. Asymptotic notation is notations are used to calculate the time complexity of an algorithm. So there are two functionalities or two methods to find the time complexity of an algorithm, right? See here, frequently count and asymptotic notation. We have discussed in the last video. So in this video, let us discuss completely about asymptotic notations. So here, see, asymptotic notations are used to calculate the time complexity of an algorithm. Okay, right? Now, coming to this asymptotic notations, we have 5 types of asymptotic notations. In the syllabus, we have about only 4. There are mainly 4 types of asymptotic notations, but this is slight easy to understand about last type also. Now, coming to see here time complexity is nothing but the time complexity in the best case, average case, and worst case too. So we need to find the time complexity of an algorithm in different cases. Okay, see, in each case, or for example you take a big ohm notation. It use big ohm notation uses a worst case time complexity completely. So we these 3 types of cases we need to individually using this different types of asymptotic notations. Okay, now coming to big ohm notation. Big ohm is nothing but it is denoted by a capital O. It is a capital O, big O. So it represents upper bound of an algorithm. First point is that it always represent upper bound of an algorithm. It always represent the worst case time complexity. See here, its upper bound is nothing but it is a worst case time complexity. Worst case is nothing but the time. See, by using an example you can clearly understand what is meant by a worst case time complexity or upper bound also. So first first we see the theory. What is the theory points in this big O notation? It's mostly frequently used in notation. It is a worst case time complexity which uses maximum amount of time to complete its execution. So see here, it is used mainly to calculate the maximum amount of time required for the execution of algorithm. So this is all about theory part. Now coming to a graphical representation. In this graphical representation we have, see here, we take t time as time on y-axis and this number of input variables, number of IP variables, number of input variables on x-axis. Now coming to time here, this is time, this is number of input variables. See here, this line is c into g of n. G of n is nothing but, see here, there are two functions in this big ohm notation. See, let us consider as a f of n is a function and g of n is another function. Now coming to f of n, see here, by explanation you can understand in easy way. We need to represent the function f of n in terms of g of n. So f of n equals to o into g of n, o dot g of n. See, according to big O notation, we represent the f of n less than or equals to O of g of n. It's nothing but it is a general form of the big O notation. See here, coming to graphical representation here, see this line is g of n. G of n, it's nothing but it is a function, and f of n is nothing but it is a worst case time complexity graph which represent as a min here, maximum amount of time which is required to complete its execution, right? See here, now by seeing an example. See here, for example, f of n equals to n square plus n. See, this is a function. This is a function. Now f of n, here see, f of n is less than or equals to c dot g of n. Here this o, take it as a constant. See here, take this o as a constant. O is a constant c, where c is greater than 0. It's nothing but it is not equals to 0 and less than 0. It is always greater than 0. And n is less than or equals to k. Here what is mean by k? K is the point where both the functions are incident or collide each other. Okay, now here where I stopped here. Now coming to this example, to n square plus 2n less than or equals to c dot g, where he, see here in this function we have n square is the highest power, right? Consider the highest power value in the place of n, because compared to this, both the n to the 2 to the power of, sorry, here n square, right? To n square is nothing but this is the highest power compared to the here n to the power of 1. So comparison of this both, 2 is highest, then consider 2 to the power of n to the power of 2. Now here we have an equation that here we need to substitute from 1 to n c values where it satisfies the entire condition. See, don't confuse here. If we substitute one value here in the place of c, if for example if we substitute here c plus here c, that's mean to n square plus n less than or equals to 1 of n square. See, is this true? No. Why? Because see here n square is not always greater than 2n square plus n, because here itself 2n square is greater than n square, and here it is n square plus n. It's nothing but 2 longer than this n square plus n is. See, coming to an example here, if we substitute 1 in n place, or if n value is 1, here 2 of 1 plus 1 less than or equals to 1 square, if we substitute n equals to 1, if n equals to 1, that means if we substitute here n value is as 1, 2 of 1 plus 1 is less than or equals to 1 square. It's 3 less than or equals to 1. It is a false condition, or it's a false statement. So substitute the c value until you get this function or entire this equation, consider as it is a true. So let us take c value as 2 and solve the problem. Here if c value is 2, here see 2n square plus n less than or equals to 2n square. See, here we have 2n square here, 2n square here. Already it is a 2n square, and here 2n square plus 1, and that is less than or it is greater than or equals to n square. That's mean it is a false condition or false statement, because already we have here 2n square and here 2n plus 1. That mean here if you send 2n square to other side, that n is less than or equals to 0. That mean here n is not equals to n. So it is a false condition. Then here consider c value. C equals to 3. Then we have that here if c equals to 3, to n square plus n less than or equals to 3n square. It is a true condition, because if we substitute any number here, for example, let us consider n value as 1. Here 1 square plus n is nothing but it is a 1 less than or equals to 3 into 1 square. It's nothing but we have this value as 3, it is less than or equals to 3. This is a correct solution. See, consider that now it is a true solution, right? Now consider that this equation is a true solution where n equals to n less than or equals to 1. That means this condition is satisfies for the all values of n less than n, or sorry, here n less than 1, n greater than or equals to 1. So this condition, up to this condition, it satisfies the entire solution of the time complexity in this big O notation. See, these calculations are somewhat confusing or difficult. Once you rewind the, or once you go back through the video and see once again this entire video, you may get clarity about this entire example. Now coming to the second one, big O notation. See here, coming to this big O notation, it is a formal method representing the lower bound of an algorithm at runtime. See here, here it is. See this big O notation, right? In this big O notation, we use upper bound. Here we use upper bound. Upper bound is, it's nothing but it is the lowest upper bound. See this 3, c of 3, consider c equals to 3 or c equals to 3 comma 4 comma entire up to n. We can also satisfy the entire condition, but we take here least upper bound. So the c values which are satisfied in that, the least count is about 3, starting count is 3, right? So we should take this least upper bound as a big O notation, which satisfies the entire condition, right? So this is all about big O notation. Coming to here, we use lowest bound. So here we use lower bound of an algorithm at the runtime. So it is mainly used for calculating the minimum amount of time required for an execution of an algorithm. So it always represent best case time complexity only. See here, in this it takes worst case time complexity, and here it uses only best case time complexity to best case time complexity of an algorithm. Now coming to graphical representation. In this graphical representation, it is, see here, it is a time taken in y-axis and number of variables taken on x-axis. See here, see, compared both graphs, it takes worst case comes down, and it takes best case, the graphs goes up. See, this is the main difference between the big O and big omega. Okay, now see here, we represent f of n in the terms of g of n, f of n in the terms of g of n, where g of n equals to omega dot g of n. Now according to big O notation, we represent that f of n is less than or greater than or equals to omega dot g of n. Here in this we use less than. That means the given function is always less than, which we need to represent in the graph, or which we need to represent the worst case time complexity. See, coming to here, we have the function n, or a function f of n is greater than or equals to g of n. That means here we took least upper bound, right? Now here we are going to take the greater lower bound. That means here, see here, f of n equals to 2 n square plus n, right? C equals to 1, where c equals to 1, we substitute as usual, we substituted here, don't confuse again. And here c equals to 1, c equals to 2, c equals to 3. So this see here, this is called least upper bound. So don't consider the least upper bound, only consider the greater lower bound. This is the greatest, it's nothing but it is a maximum amount of, it is a minimum amount of time required for an execution. That means, see here, this 2n square plus n greater than or equals to 2n, consider as condition satisfies the entire n less than or equals to 0 condition. That means this c equals to 0, when constant c equals to 0, that represents that it is a lower bound which is used to calculate the minimum amount of time required for an execution. Okay, clear? Here it takes lowest upper bound, here it takes greatest to lower bound. See here, c equals to 1, it is also a lowest, sorry, it is also a lower bound, but compared to both, greatest upper bound is 2 here, so we consider 2 as a greatest upper bound. See, coming to here, we calculated some calculations, right? Same as it is, we calculate here also, to n square plus n greater than or equals to, for example, c value we take as 1. If we c value is 1, it written as n square, that mean if of 2 of 1 square plus n less than n is nothing but 1 and 1 square, right? Here it is 3 greater than or equals to 1. This is true condition, right? So according to this function, or according to this condition, we calculate the c values here, and we find the greatest lower bound. Greatest lower bound is nothing but it is a 2 c equals to 2. Here we calculated entirely. Now here we calculated the time complexity of an big omega notation, right? This is all about big omega notation. Now coming to theta notation, here it is a formal method to represent the average bound of an algorithm at the runtime. The entire concept of theta notation is completely of the combination of big O notation and big omega notation, right? It is mainly used for calculating the average amount of time required for execution of an algorithm. So it is take average amount of time to complete the execution of an entire algorithm. Now it represents average time complexity. See, it represents average time complexity. It's nothing but exact time. So it gives the exact time of it's nothing but time complexity of an algorithm to complete the execution. Now here in this graph, it is a graphical representation, right? Now here on y-axis we take time, and x-axis we take number of variables as usual. We represent f of n in terms of g of n, right? Now here, see here, f of n equals to theta dot g of n, and according to theta notation we represent. Here we use three functions. In these three functions, see here, the main function is one function, and other two functions are, one is about worst case and one is best case. By using this both functions, we design a graph here. See, this is the best case. See, one second, I need to check. So this is the best case and this is the worst case. This is the best case and this is the worst case. This both combinedly with together write as a average case. Average case time complexity. See here, for example, we take here, same example we need to take here, and here see c of 1 n square less than or equals to 2n square plus n less than or equals to c2 n square. That means here we considering the function lies between the function c1 and function c2. That means by substituting the here we got lowest upper bound is 3, and here we got greatest lower bound is 2, right? See, this is the greatest lower bound and this is the lowest upper bound. By combination of this both, see, it is a combination of big O and big omega notations. So see, by this we clearly know that if we substitute these values in this equation, it satisfies the completely of all these three functions will be equal, or which it satisfies the entire condition. That's all. So now coming to At ohm notation, it is represented by the small o. See, I forgot to say that. See here, this big O notation was represented by omega, and here theta notation was represented by theta. Now, see, it is represented by small o. It is as same as big O notation, but instead of taking the lowest upper bound, we take only upper bound. It's nothing but it is, for example, here O notation. Here, what are the lowest upper bounds here? Lowest upper bounds are from 3 to entire 3, 4, 5, so on. So here we take not only 3 but also 4, 5, 6, any of these numbers. So this is completely of about see here, we need not to be take 3 in this particular example, because here, see here, it is 3 less than or equals to 3, but here we need not to be take 3, we take from 4, because here f of n is only less than small o g of n, not, this is not less than or equals to, just it is less than, f of n less than. So we need not to be take 3, from 4 we can take for this only particular example, not for all examples. See, for example, here we take 2n square plus n less than or equals to cn square. That's nothing but here we take c equals to 4. That means 2n square plus n greater than 4n square. This is the solution of this little ohm notation. Coming to little omega notation, it is as same as big omega notation, but it instead of taking greater bound, we take lower bound. Lower bound, we take lower bound. That is nothing but in this particular example we can take here c equals to 1 and c equals to 2 itself. 2 also we can take. See, for example, here let us take c to n square plus n greater than 2n square. This is absolutely right answer. So because here 2n is always greater than 2n plus something, right? So this satisfies the entire condition. This is all completely about asymptotic notations. See, so this is all about completely first part of design and analysis algorithm. In that first unit we have 2 parts. So we have completed first part, and in the next video I continue about the second part, which is all about divide and conquer methods. So that's all in this video. Make a like, share and subscribe. Don't forget to subscribe to our channel, and thank you for watching.